Okay, we're going to learn today about carbohydrates. Carbohydrates are sugars or saccharides and the polymers therefrom. So the building blocks are the polysaccharides, the polymers of these things. The building blocks of the building blocks are the monomers themselves. The reason for this lecture, if you're the first time, if this is the first one in the series that you're joining in on, is because a video came out by Dave Farina, video entitled Elucidating the Agenda of James Tour, A Defense of Abiogenesis. See the description box below for the link. After watching that video, I was confused about almost every slide and statement that Dave Farina presented. There were numerous gross scientific inaccuracies in his claims, in my opinion. Since others might be likewise confused, I will use the Farina video with timestamps as the launch points for this series of lectures. So in other words, you'll see timestamps. You'll see something that says like 2.43, and that means at 2 minutes and 43 seconds, this is what was said in that video. Just because others might be confused too, so we'll use that to launch the discussion. I'm thankful to Dave Farina for attempts to teach the layperson about scientific topics on his YouTube channel. Professor Dave Explains is what his YouTube channel is for. So I give you a shout out for that, Dave. That's a commendable endeavor. I therefore seek no contest with Dave Farina, only clarity. I'm not trying to contest with Dave Farina. I'm trying only to bring clarity. As a synthetic chemist, I want to come into this and build some clarity here. I have no contest with Dave. And I have nothing negative to say about Dave Farina. On this video, I just want to point out some inaccuracies on things that were taught, that maybe I can bring some light here. All right. Other synthetic chemists can comment and point out where I'm correct or incorrect. I particularly invite a critique from my synthetic chemist colleagues and students studying synthetic chemistry and those studying origin of life. If disputing, please reference a literature article so I can read and learn along with you. All right, polysaccharides can also be synthesized. That's what it said in that video. The individual units can connect in different ways. So he wrote that. All right. In 7 minutes, it says, some think
carbohydrates are a bit more complex since, despite consisting of the same monomer over and over, they can connect in a number of different ways. So synthesizing polysaccharides is trickier, though we are making progress with that too.
All right, so these are tricky to synthesize, it was claimed in that video. And carbohydrates consist of the same monomer over and over. It would be hard to be more wrong on that. It would just be hard to be more wrong because there are many different carbohydrates, as we're about to see. And so you get mixed polymers where one inserts and not another. And yeah, there are different ways to connect these that they don't just easily hook on at the end over and over again. It says in 730, and some say
any biomolecule is easy to synthesize. Jim knows this. He's a synthetic chemist. What he probably means is that we haven't seen these biomacromolecules form spontaneously outside of a biological system. But that's not what he says.
Quoting that video, any biomolecule is easy to synthesize. That is so wrong. He says, Jim knows this. I didn't know that. I think the vast majority of biomolecules are really hard to synthesize, especially if you want to try to do it in homochiral form. He's a synthetic chemist. What he probably means is that we have not seen these biomolecules form spontaneously outside of a biological system. But that's not what he said. Well, first of all, every video where I've spoken on this has been a video on abiogenesis. The questions were abiogenesis. So when you pull one sentence out of context, yeah, you're going to get that. But nonetheless, even the ones that are synthesized. You want to make a peptide? Where do they get the amino acids? They get them all from nature. They don't go ahead and make those amino acids from scratch in homochiral form or from methane. They don't make them. They don't make them from scratch. Every one of their basic building blocks, they're taken from nature anyway. They're breaking down the polymers into the monomers, and then they resell the monomers and people rebuild them back into polymers. So all the building blocks for the building blocks were made by nature anyway. They're not easy to synthesize. Making homochiral amino acids is not an easy thing to do. Making homochiral carbohydrates is really, really hard to do. Really hard to do. And we'll look at modern methods for making those, not prebiotic methods. They're really hard to do. So this statement, any biomolecule is easy to synthesize, is as wrong can be. That is probably the most wrong statement in that entire video that we're looking at. That is the most wrong statement. Any synthetic chemist is going to probably just be getting up out of their chair right now because their palpitations cause them to collapse on the ground to hear a statement, any biomolecule is easy to synthesize. I didn't know that. He says I know that, but I didn't know that. And just because he's not seen these biomolecules form spontaneously outside of a biological system, but that's not what he says. Whoa. Oh, man. I said enough on that. All right. So here's some naturally occurring monosaccharides. Remember he said there was one saccharide over and over? These are all the naturally occurring. These are just some of the naturally occurring monosaccharides. So you have a lot of them. A lot. Here are homopolymer saccharides. So there are some saccharides that will repeat with the same unit over and over again. They're called homopolysaccharides. But there's a lot of polysaccharides that are not homopolysaccharides. But they have, this beta means that there's an orientation pointing upward at the 1,4 position. That doesn't have to be 1,4. It can be at a different position. For example, it can be at a 1,3 position. It can be alpha or beta. All these make it really, really complex to make these things. Really hard to hook these things together. I'm going to show you that. This is just crazy hard. All right, to make nucleotides, one has to make ribose. So if you want to make a nucleotide, say you want to make RNA, you can't make RNA without first making the carbohydrates. The carbohydrates have to come before you can make DNA or RNA. Did you know that? Because they're made of a sugar. For a carbohydrate, how do we choose? Take, for example, the pentose sugar, one of the more common carbohydrates and that used for DNA and RNA. Pentose sugars have 3 stereogenic centers, so 8 possible isomers. So this is in the open form. They have 3. If they're in the closed form, they're going to have 4 stereogenic centers. So it'd so instead of being 2 to the 3rd, it's going to be 2 to the 4th possible isomers. We'll see more of that. And all are chiral, meaning that they all have a non-superimposable mirror image. But what if we do not know the target? Then the complexity of the problem would certainly be more compounded, and mixtures are problematic. So here's the different isomers here. Here's the 8 different isomers. All of these isomers can possibly be forming. All of these isomers can be possibly forming. So it's not just one pair of enantiomers. It's these 8. How do you do this? How do you make this in a pre-biological sense? Specifically, we need a 5-carbon sugar, or D-ribose in particular, selected from the set of 8 possible isomers. Further, for DNA, it has to be 1 hydroxyl group deficient, or deoxyribose. If it's not, then it'll be suitable for RNA, but far less stable. But prebiotic systems never knew any of this. There was a blinded pathway to a host of products, somehow selecting the one desired long before any selecting agent could have been biologically available. And what are the selection criteria? It's hard to know if we do not know the target. The prebiotic problem is hard. And even if the target were known, the selector would be another molecule, at least as complex as the desired analyte. And what was the selector? So remember, this is prebiotic. There is no selector. There's nothing to select the right one out. You're going to make all of these isomers when you do the foremost reaction. So how do you select the right one There was a statement in that video talking about the Cannizzaro reaction. So I've always claimed the Cannizzaro reaction versus the foremost reaction needed in making carbohydrates. If you're going to use the foremost reaction to make carbohydrates, you're going to be competing with it and decomposing your compounds by the Cannizzaro reactions. But in that video,
he also refers to a specific reaction called the Cannizzaro reaction, which requires strongly basic conditions. He knows these conditions are required, and he knows the ocean did not provide such strongly basic conditions, so I don't know why he brings this one up at all.
So someone in that video says that Jim, he's talking about me, knows that the Cannizzaro reaction is irrelevant because the ocean can't do that. So are we restricting synthesis only to the oceans? Later on in the video, the same person says that these evaporating pools are his favorite reaction vessel. The Cannizzaro reaction competes with the foremost reaction. Of course it's a problem. How do I know that? Well, right here it says, this is just from Wikipedia, you don't have to go far. Calcium hydroxide is produced commercially by treating lime and water. So you just take lime and water, you get calcium hydroxide. This should actually be calcium OH taken twice. The mineral form portlandite is relatively rare, but can be found in some volcanic, plutonic, and metamorphic rocks. So hydroxide, calcium hydroxide is available. Look at that. There's the foremost reaction. 1861, done with calcium hydroxide. Foremost reaction can be done with calcium hydroxide, same way that Cannizzaro reaction can take place. They are competing. And so you see here it also says under the Cannizzaro reaction and under the foremost reaction on Wikipedia, it must be carefully controlled, otherwise alkaline conditions will cause aldoses to undergo the Cannizzaro reaction. So the very synthesis that makes the very Cannizzaro reaction that Breslau came up with in 1959 has the competing the very foremost reaction has the competing Cannizzaro reaction. It's further shown here in 1973, Journal of Catalysis, 1974. It says, the foremost reaction, the homogeneously catalyzed condensation of formaldehyde to sugars, proceeds simultaneously with the Cannizzaro and cross-Cannizzaro reactions. And it is postulated that calcium hydroxide is the actual catalytic species, the calcium hydroxide monohydroxide. So that's why maybe those of you who are watching can understand why every slide I was wondering, why is this being said? Why is it being said? It's totally inaccurate, and you don't have to go far to see how inaccurate it is. You just go to Wikipedia, and it's right there. You didn't even have to go and find this article in the literature. All right, so a man named Eschenmoser, Albert Eschenmoser, who's a superb chemist. I've admired him since I was a graduate student. He is an excellent chemist. He tried to make the pentoses by a prebiotic route, starting with formaldehyde or glycoformaldehyde. He started with glycoformaldehyde because he didn't want to have to worry about doing the photocoupling of formaldehyde. But starting from glycoformaldehyde, he tried to do this. Let's see the troubles that he had. Recognizing that carbohydrates, and I'll show you the references on this so you'll be able to look this up if you want to. Recognizing that carbohydrates are the key building blocks, and in particular the 5-carbon pentoses, since they form the scaffolding for both DNA and RNA, Eschenmoser spent years suggesting the prebiotic routes to those compounds. The direct synthesis of the pentoses was not successful when starting with a presumed simple natural precursor, glycoaldehyde, and using the foremost reaction, which is the base catalyzed coupling with formaldehyde in the presence of a divalent cation such as calcium. Cleverly, this is human insight going into prebiotic world. Cleverly, Eschenmoser, being the master synthetic chemist that he is, did not start with formaldehyde or its dimer, glycoaldehyde, but with the phosphorylated glycoaldehyde to make it more suitable coupling partner. How convenient. He didn't start with what was available on prebiotic earth or the photocatalyzed coupling of it, because you can see here, here's this photocatalyzed coupling here. photopromoted coupling. But he started with the phosphate already on there. Now, might this have formed on the Earth? Well, I guess if sunlight hit this long enough, made this, and this then got the phosphate on there. But why don't you try to do this step in the laboratory too? It's more convenient to just buy that. That's why. Prebiotic Earth can go find its own. Since glycoaldehyde is the dimeric form of formaldehyde, one would first have to make the dimer of formaldehyde and stop there prior to further chemistry taking place in the foremost reaction. Nonetheless, a good organic chemist can design conditions to isolate the product purified and then proceed as Eschenmoser did. Can phosphorylation then occur? Sure, under high concentration of phosphorylating agent, but not in the presence of a strong base, such as required for the formation of the glycoaldehyde itself. So the glycoaldehyde needs strong base, then it needs to find itself away from the strong base to stop the reaction. While away from the strong base in near neutral solution, it was phosphorylated with 4 molar equivalents of amido triphosphate in near neutral aqueous solution, while further in the presence of magnesium ions. How convenient. Now that proper phosphorylation is complete, the glycoaldehyde phosphate is isolated and purified. Eschenmoser then exposed the isolated and purified glycoaldehyde phosphate to 2 normal sodium hydroxide. Where did that come from? And in that video it said that hydroxide's not available in the oceans. I don't know if it's available on the oceans, but we even saw references. It is available on early Earth. And it would have been available at a concentration of 0.08 moles per liter. So the starting formaldehyde was in strong base, then the product isolated and liberated from the strong base, then exposed to a neutral solution of the amido triphosphate, which the researchers made separately. Then they isolated the product, glycoaldehyde phosphate, and conveniently exposed it again to strong base. Even with all this masterful design, the mixture did not produce the desired pentose, but mostly racemic hexose triphosphates. So even with all of this amazing treatment, Eschenmoser couldn't make the pentoses that he wanted. Then, using a stroke of superb synthetic insight, Eschenmoser placed the glycoaldehyde phosphate in the strong base and added 0.04 moles per liter of formaldehyde to obtain 40 to 50% yield of, quote, mostly, unquote, racemic pentose diphosphate, the 8-component mixture showed before with the 2 phosphates at C2 and C4 of the structure. So he got all the racemic pentose. He got all 8 of them. That means there were 8 possible isomers, 4 diastereomers, in that 40 to 50% yield mixture. The desired racemic ribose 2,4-diphosphate, that's the one he wants, 15% of the total from the reaction. Racemic arabinose 2,4-diphosphate, racemic lycose 2,4-diphosphate, and racemic xylose 2,4-diphosphate, where racemic signifies a 1-to-1 mixture of the 2 enantiomers, along with 11 other identified carbohydrate species, all bearing their enantiomeric partners, meaning 22 other identified species from the 40 to 50%, with the other 50 to 60% being unidentified, non-volatile compounds such as higher oligomers and polymers. What a mess! Even Eschenmoser did not attempt to separate out the desired, albeit still racemic, ribose 2,4-diphosphate, because the separation would have been nearly impossible. The relay synthesis ensues, but that's cheating. So let me explain what he did. He ran a reaction, he got a little bit of what he wanted, a trace of it, and he got a bunch of other stuff. He himself couldn't even fish that thing out. It would be so hard to fish it out because the related structures are really related, and then you got a lot of polymers and other oligomers. But somehow, that very clever early Earth was able to do that. And so then what did he do? He just bought the compound he wanted. That's the relay synthesis I'm talking about. Origin of life researchers do that all the time. Regular organic synthesis, you don't do that. People would say that's cheating. This is done all the time in this field. Why? Because they have to, because the mixtures you get from prebiotic conditions are just terrible. Even the expertise of the researchers involved, the data more easily argue that any related prebiotic process is unlikely to afford the requisite carbohydrate building blocks. Their results better argue against this being the root, since such careful controls had to be enacted by the masterful synthetic chemist to afford even gross mixtures of products that were unuseful, I should add. In many of my talks, I say time is a problem because chemists fish out their reaction as soon as the highest yield is obtained. Because if you let it go, it just continues to make unidentifiable polymeric products, as 50 to 60% of Eschen-Moser's stuff showed. But in that video, it was said, it quoted me, and it quoted where I say that abiogenesis, time hurts it. Time is the enemy. Well, time is a problem. Here's an example of this. So in the video, it was said that time is not a problem, that I don't know what I'm talking about in this thing. Well, you can look that up. The timestamp on that is 15 minutes and 54 seconds. We'll come back to that. But anyway, time is a problem. Furthermore, Eschen-Moser teaches that, quote, the total amount of the 4 diastereomers is largely unchanged, quote. But that is not entirely correct. So if you look in his article, he says the total amount doesn't change much. But that's not entirely correct. Because when I looked at the experimentals, this is what's written. His own data show that the combined yield of the 4 diastereomers dropped from 34% to 30% over the course of an additional 22 weeks. Hence a relative 12% loss of the pentoses over 22 weeks. Thus, after a few years, which is a brief moment in time by prebiotic terms, there would be little, if any, pentoses left, let alone the more rapid loss of the desired ribose 2,4-diphosphate. Where does the material go? Likely to extended oligomers and polymers, which is common in organic reactions, and especially common in extended aldol-based processes, proceeding to the point of being insoluble in the solution or generating a viscous mixture of ill-defined polyols. It was argued in that video that these reactions are all in equilibrium and they go forward and back and forward and back. That's just not true. There's the reference, by the way. And that's just not true. They can go forward and back, but if the equilibrium constant is not 1, they favor going in one direction. Once they've gone there, they can favor going in another direction. So when the equilibrium constant is large, it doesn't go back. It just doesn't go back. Not everything has an equilibrium constant of 1. After all this work on the pentoses, which mimic those seen in nature for DNA and RNA, Eschen-Moser chose to switch to what he called homo-DNA, an oligonucleotide composed of a D23 dideoxyallopyranose, a 6-membered ring, instead of DNA's 2-deoxyribofuranos, 5-membered ring for the carbohydrate backbone. This gave him added stability needed for his subsequent base pairing studies. He humbly conceded that, from an etological perspective, the work on homo-DNA was regarded as a model study only, albeit one that proved to greatly facilitate our entry into base pairing prognoses, the development of methodology for the oligonucleotide preparation, and the interpretation of base pairing characteristics of alternative nucleic acids, unquote. Prebiotic chemistry is just very hard. What did all that gobbledygook mean that he said? It means that he couldn't get what he wanted, so he wanted what he got. That's what it meant. He couldn't make the 5-member ring, but he could make the 6, so he worked with that, and that's not what nature used. Nature used the hard one. Used the 5. Prebiotic chemistry is extremely difficult to perform even for the world's best synthetic chemists like Eschen-Moser. So he chose the more convenient model study. Reagent addition order is critical, as seen in the detailed experimental protocols. In other words, A needs to be added before B, and then C, and each at its own specific temperature to effect a proper reaction and coupling yield. The parameters of temperature, pressure, solvent, light or no light, pH, oxygen or no oxygen, moisture or no moisture has to be carefully controlled to build complex molecular structures. Unless one can devise sophisticated promoters or catalysts that are stable in air and moisture and can work at common atmospheric conditions, precise control must be maintained. The characterization at each step is essential, and even more so if we're going to have to bring up more starting material in the synthesis. Therefore, small changes in ultimate function demand major rerouting in synthetic approaches. All changes when doing chemistry are hard and cannot be done through hand-waving arguments or simple erasures on a board. Laborious and intentional elements of forethought are required. More sophisticated proposals to prebiotic feedstocks have arisen since the often quoted work of Eschenmoser. It is generally proposed that there must have been a chemical means to generate an information-bearing molecule such as DNA or RNA. Since the 1960s, many have suggested that the polymer is RNA rather than DNA, leading to the RNA world hypothesis. Aside from the fact that the RNA backbone is very unstable relative to DNA, chemically activated ribonucleotides, through careful manipulation of the structure, can polymerize to form RNA, but of course with no prescribed sequence. And as observed by Eschenmoser and many others, the coupling of ribose with the nucleotide is the first step, and even those engrossed in prebiotic research have difficulty envisioning that process, especially for purines and pyrimidines. Sutherland and co-workers have insightfully proposed that pyrimidine and ribonucleotides can form short sequences using a ribose amino oxazoline and an hydronucleoside intermediate, all from simple compounds such as cyanamide, cyanoacetylene, glycoaldehyde, glyceraldehyde, and inorganic phosphate. The use of inorganic phosphate changes the previously proposed basic conditions to pH-buffered solution, therefore slowing decomposition pathways. Okay. So, if making the saccharide, the sugar, we'll talk about RNA and DNA later. If making the saccharide, the sugar, was not hard enough, polysaccharide problem, hooking sugars together, is just as hard. So he couldn't make the saccharides, the basic building blocks. Nobody has made saccharides by a prebiotic route. Nobody has made the sugars, the carbohydrates, the basic building block, the sugars, the pre-building blocks. Now you've got to somehow hook together to make those a building block. Nobody's made those by a prebiotic route either. Disaccharides. So here's some lessons in chemistry. Disaccharides consist of two monosaccharides connected together by a glycosidic linkage. That's the glycosidic linkage. That's the beta linkage because it's above. If it were going down, it'd be the alpha linkage. And so you can see that this is the 4O, meaning that this is on the 4 from this unit, the fourth unit, 1, 2, 3, 4, the 4 oxygen of beta-D-galactopyrinosyl D-glucopyranose. That is defining for us that this is a beta linkage coming off the 4, and this is a glycosidic linkage right here. That's all kind of embedded in the name. And this has a common name, lactose. Lactose is a galactose unit hooked up to a glucose unit. So remember in the first slide when we were told that it's all the same unit, it's just the same unit stuck on?
Carbohydrates are a bit more complex since despite consisting of the same monomer over and over,
here's a disaccharide. It's two different units. You see, this has got the OH at the 4 position down, this has got the OH at the 4 position up. These are two different saccharides. I tell you, every slide in that video was mind-wrenching and heart-wrenching for me. It was just difficult. It was just hard because every slide, I'm just telling you, every slide had something wrong in it. The disaccharides. Here's another disaccharide. Again, are these? This is a glucopyranose and a fructopyranose. Are these the same units hooked together? No. And so here you have a 6-membered one hooked up to a 5-membered one. Here's an alpha linkage with respect to this, and a beta linkage with respect to this. And so you know, this is how they can hook together. This is really complex. Now, why did they hook in here? Why didn't this hook to this site, or this hydroxyl, or this one, or this one, or this? That's the big question. There's all these free hydroxyls. Why are they hooking up here, not? That's the problem with carbohydrate synthesis. There's so many different tentacles. It can stick up at any place. That's what makes the chemistry. You're going to see the synthetic way, the ways that chemists today, the torture that they have to go through to make these things. How did this happen on a prebiotic earth? First of all, we don't know how to make the saccharide. We don't know how to make it homochiral. And then even if we could, we don't know how to purify it. And then even if we could, we really don't know how to hook them together. In the video, it was said it's tricky.
So synthesizing polysaccharides is trickier.
It's tricky? It's tricky? Nobody knows. Nobody knows how to do that in any prebiotic route. Nobody knows. So it's a lot more than tricky. It's unknown. We remain clueless. Sugars with many monosaccharide residues connected by glycosidic linkages are called polysaccharides. Cellulose is a polymer of glucose connected by beta-1,4 glycosidic linkages. So here's glucose, and they all have this beta-1,4 glycosidic link. Predominantly, they have this. So they have this, so this is cellulose. This is the general structure. They're made up of glucose hooked together, and it's because of these linkages that you and I don't normally eat wood. You know, we don't digest that really well. We don't normally go out and eat grass. We don't digest it very well. I mean, it could be good fiber, but we don't get much nutrition from it. It doesn't break down in our body to glucose and feed our body, but it does in cows because they have microorganisms that can break this spawn and break it down to this general structure, this general small sugar structure. And so we don't get much out of this. We got to have another linkage here. So starch. This is what we eat. Starch. You see that this is coming at the alpha linkage, not the beta linkage. So it's this same sort of structure, this same glucose polymer that was in cellulose, but with it going alpha. Then we can digest it. And so this is why we eat starch and we don't eat wood. This is why, because it has this linkage. But you see, they also have branches. Occasionally there's this 1,6 linkage. How do you do that? If you wanted to make a starch molecule, how do you do that? Nobody knows how to do that. Nobody knows. It's not just tricky. Nobody knows how to do that in any prebiotic structure. And if you had that many linkages that you see here, I don't think anybody's ever made anything like this synthetically. That's way hard. We'll show you that. Anyway, so here's D-glucose. So D-glucose, and these are ways that D-glucose could be stuck together from all of these different positions. These can be all, and sometimes it can cyclize into a 5-member ring, sometimes into a 6-member ring. It can be hooked up from all these different positions. If you just take D-glucose, it can reside as the 6-member ring, it can reside as 5-member rings, it can reside as the open system. This has got 4 stereogenic centers, so this has 2 to the 4th possible isomers. When it's cyclized, it has 5 stereogenic centers, so each of these has 32 possible isomers. Remember all that goop that Eschenmoser made? That's what you would get with this. You get 32 possible isomers plus all the polymerization adducts of these. Nobody knows how this was made on prebiotic Earth. So how do Origin of Life people deal with it? They just buy these? Well, where does the manufacturers, where do the people who sell these get it? Well, they get it from nature, because nature just spits these things out. Biology is amazing. Nobody knows where it came from on prebiotic Earth. You see why it's frustrating to have people just trivialize this stuff? So if we just take 6 repeat units of a reducing hexasaccharide like D-glucose shown, this is just 6 units. How many ways could you hook this together? Because in the video says it just keeps hooking on to the end. That's what it said. Well, here's the number of ways. More than 1 trillion different ways that you could hook this together. Just through, because this glycosidic linkage can change to an alpha or beta, and these, just by the different branches, see it has all these tentacles, just 6 units of the same sugar. 6 units of the same sugar can hook together in over 1 trillion ways. Do you know how big 1 trillion is? Let me point this out to you. 1 million seconds, 1 million M, is 11 days. 1 million seconds is 11 days. 1 billion seconds with a B is 32 years. It's a difference between a million and a billion. 1 trillion seconds is 32,000 years. A trillion is a big, big number. 32,000 years for a billion seconds. There's over, for a trillion seconds. This is over 1 trillion ways you can hook this together. So if you just let this go randomly hooked together, you'll never get what you want. And if you get something and you try to do it again, it'll never make the same thing again. This is hard chemistry. This is why when people trivialize this stuff, they sadly don't know the area. And they speak so confidently because they don't know the area. This is just from Wikipedia. You just look on Wikipedia. You say, how do people synthesize carbohydrates? Look at all the steps. So here you start. You start say with just this hexasaccharide. So you start with this thing here. Now, look at all the steps you have to go through before you do any building of the structure, just so that you can block certain groups on it. And then you start doing all of these steps just to do that one little change. These are all human-made steps. And then all of these steps just to do this one little change. And this group's going to end up coming off anyway. And then you do all of these steps on it. You do all of these steps to do this. And then you start hooking these together. It's just crazy hard chemistry. Okay, so just in my normal literature reading, because I knew I was going to have to prepare a video on this, I just came across this article. So this is some September 17th organic letters. So they want to make this known as saccharide. They want to make this saccharide, this 9-sugar saccharide. And so they want to do this, and this mimics some natural product or something that they want to make. They want to make this. And so how do they do this? So you see here, they have these different pieces that they're going to make, and they're going to stick these together. And it's based on former work. So how do they do this? So you start from the material. So this is what they want to make. This has just 9 sugars. Now let me tell you something. Naturally occurring sugars are huge. They are displayed all over the surface of a cell. If you have the structure of those wrong at all, the cell dies. Every problem in a cell can be traced back to a carbohydrate problem. There are carbohydrate problems involved. If you get the wrong structure on these things, it's just death to the cell. Well, how would you make this? Well, if you work your way back, you might be able to break it up. This is just mind confined. Break it up into these structures and work your way back to these structures. So that's retrosynthesis. And then you start looking at the synthesis. So we're going to start from number 10, this compound, which somebody had made formerly, and they bring it through all of these steps. And this is a silicon reagent. These are all human-made reagents, benzyl chloride, and you get certain yields here, and trifluoroacetic acid is going to bust this off. They're going to put a silicon group back on here. And then they're going to start with this compound, which had been made previously by somebody else, and they're going to bring this through a certain number of steps with an iridium catalyst, and mercuric oxide, and mercuric chloride, and benzyl bromide, and all these deprotection steps. So you do this. Now, then you take those pieces and you go through and you do through all of these other steps to try to build this thing. This is hard chemistry. And that's overall to make this compound, it was 16 steps in 4.4% overall yield. 4.4% overall yield. Modern synthetic chemistry using all the ingenuity of humankind, using reagents that never would have been available on a prebiotic Earth. You get 4.4% yield. And that was multiple separations to get this. But they started with already advanced intermediates that had already been made before. So this has 90 pages of synthesis and characterization data behind it. So you just have the article, and then there's 90 pages online of the synthetic procedures that are needed to do this. Like, what kind of procedures? How would you do something like this on an early Earth? But it says, to a stirred solution of compound 22, 1.12 grams, 1.35 millimoles in dry tetrahydrofuran. All of these are human-made reagents. 24 mils, degassed under vacuum, something you can't do on an early Earth, and stirring under an argon atmosphere. 1,5-cyclohexadiene bis methyl diphenylphosphine iridium 1 hexafluorophosphate catalyst was added, followed by further degassing of the reaction mixture. The suspension was stirred for 15 minutes at 0 degrees. The catalyst was then activated with hydrogen for 2 minutes in a hydrogen atmosphere. The excess hydrogen was removed by 3 cycles of vacuum argon. The reaction mixture was then stirred for 2 hours at room temperature under argon atmosphere. The solvent was evaporated and the residue was dissolved in acetone water 10:1, 11 mLs, before mercuric oxide 410 milligrams and mercuric chloride 440 milligrams were added. The reaction mixture was stirred for 2 hours at room temperature and then the solvent was concentrated and the residue was diluted with ethyl acetate 150 mils, washed with 10% potassium iodide, saturated sodium sulfate, and water. The aqueous layers were extracted with ethyl acetate and the combined organic layers were dried over sodium sulfate, filtered, and the filtrate was concentrated. The crude residue was purified by flash chromatography, 4:1 hexane ethyl acetate to afford 23 and 82% yield as a syrup. And then it gives the characterization data. And then here's the characterization data. How did early Earth pull something like this off? And you think we've got all this figured out? You see the frustration that occurs? This is why I want to teach people that this stuff is so hard. But remember, his 4.4% yield, this is one of the advanced precursors. He started from multiple advanced precursors, but this is one of the advanced precursors he started with. So literature methods were used to make several of his precursors, but let's just take one of them. So this was prepared separately using other known procedures. It wasn't even described in those 90 pages. Well, we look up that reference. Compound 15 was in reference number 15. You look it up. Here's the reference. All right? And so you look it up, and that is described. They say see scheme S4. That means supplemental page 4. So you go to the supplemental of this reference, and you find 105 pages. 105 pages, in addition to those other 90 pages of those sort of little procedures all referenced out. And here's the procedure. 105 pages. And so here's the synthetic scheme. To get this, so here's the synthesis, here's all the synthetic steps you got to go through. And I cut it off here. I just cut it off. I mean, I don't want to put you to sleep. Look, some people are going to love this video. Other people are going to say this video is the perfect cure for insomnia. I understand that. But just bear with me. I want you to feel my pain. Feel my pain when people suggest we understand how to do this. All right? So here's what they had to go through to make this compound. This is but now you go through but they're starting from here, and so this is what you got to go through. Plus 9 more pages of characterization data on top of this. But then look at that. In this paper, they didn't start from something that you can buy. You had to make this. Well, how do you make that? You can't buy that. How do you make that? Well, you got to look up in this article. So you go to this article. This is what it looks like to go through the primary literature. This is not easy. So you look up that article. And then our article, you find this article, here's the article, and there is that compound. So there they made that compound, and that compound conveniently goes back to D-glucose. Ah. Well, did they make D-glucose? No, they took it from nature. If they had to make D-glucose, it would have been super hard. It would have been another 300 pages that's trying to make D-glucose. And these are using advanced synthetic methods, not a prebiotic earth method. And so to make this, you got to go through all of this stuff. Here's the experimental procedures where you got to go through all of these steps just to make this. So here's all the transformations. You start with D-glucose just to make this intermediate. So in summary, carbohydrate synthesis is exceedingly hard. These are the hardest of all the compounds to go through. Carbohydrates have more embedded information in them than DNA and RNA combined because of all the ways that they can hook together. If you just think of oligonucleotides, if you had the same same A nucleotide and you wanted to hook this together, how many ways can you hook that together? One way, A. But if you wanted to hook 6 D-glucoses together, it's over 1 trillion ways you could hook that together. So it's much more embedded information in these. And that doesn't come from the original DNA template alone. There are other enzymes from exogenous DNA working on that, modifying those carbohydrate structures on the fly throughout the cell life as different enzymes, different reagents come down on the surface of a cell, modifying the structures. It's really amazing. It's really just amazing. All right, coupling of carbohydrates together is painstaking. It's not tricky, it's painstaking. The untrained have no idea how hard the syntheses are to perform. They're just clueless. That's what I'm saying. They're just clueless. And this is why they can speak so confidently about this stuff, because they just don't know. The trained remain clueless on how these could have formed in a prebiotic system. The untrained see little difficulty in conducting these syntheses. So, anyway, that's the end. That's the end, and that's where we are. So, what have we done? Just to remind you, I gave you an introduction on what's abiogenesis. We talked about the primordial soup and what do lay people understand in this. Hype from the origin of life researchers themselves. I gave you a lesson on what chirality is and homochirality. I gave you, and now we just talked about carbohydrates. So we still have a number of different things. I still have to go through the peptides, the nucleotides, and go through some intermediate summary, and then lipids, and then chiral-induced spin selectivity, constructing a cell, and then some summary after that. But we'll get through this together. Thank you for bearing with me. If you're interested in seeing more of these and you're not letting to sleep, you can subscribe right here, and we'll ding you, and you can watch the next video, which should be coming out soon. Thank you. Thanks for joining us. If you want to subscribe, just click right here, subscribe, and we'll give you a shout out when the next video in this series comes out. Okay, Ryan, I think I'm going to call it a day.